Imagine falling through space in a straight line, drifting past the last galaxy you will ever see, and then simply continuing. No stars ignite ahead of you, no galaxies drift into view. For a distance so vast that light itself would need hundreds of millions of years to cross it, there is nothing but a black, silent gulf. This is not science fiction. Regions like this actually exist, carved into the fabric of the universe itself. And astonishingly, some scientists now suspect that we ourselves might already be drifting inside one without ever having noticed. To understand what it would mean to fall into the largest void in the universe, we first have to unlearn something most of us assume without ever questioning it. That space is basically uniform, that if you travel far enough in any direction, you'll eventually bump into another galaxy, another cluster, another pocket of light. For a long time, even astronomers believed something like this. But starting in the late 1970s and early 1980s, as telescopes became powerful enough to map not just the positions of galaxies on the sky, but their distances as well, a strange picture began to emerge. Galaxies were not scattered randomly like grains of sand thrown across a table. They were arranged in something closer to a cosmic web, long filaments of galaxies stretching across space, intersecting at dense nodes where galaxy clusters pile up, all of it forming sheets and walls with enormous, mostly empty pockets in between. If you have ever seen a cross-section of a kitchen sponge or a close-up of the bubbles in a glass of beer, you have a rough mental image of this structure. The galaxies live on the thin walls and filaments, the froth of the cosmic sponge. The interiors of the bubbles are the voids. And voids are not just occasional oddities. They are, by volume, the dominant feature of the universe. Roughly 80% of the entire volume of the observable universe is taken up by these vast, low-density bubbles. We tend to picture the cosmos as a glittering sea of galaxies, because that's what we can see, and that's what fills our imagination, shaped by images from the Hubble and Webb telescopes. But if you could shrink yourself down and randomly teleport to any coordinate in the universe, the overwhelming odds are that you would not land near a galaxy at all. You would land in the emptiness between them. The most famous of these emptinesses, and for a long time the reigning record holder for sheer size, is a region astronomers call the Bode's Void, nicknamed, rather dramatically but accurately, the Great Nothing. It was discovered almost by accident in 1981 by the astronomer Robert Kirshner and his colleagues, who were using a new generation of redshift surveys to build a three-dimensional map of galaxies in a patch of sky near the constellation Bode's. Redshift, for anyone unfamiliar with the term, is essentially a distance and motion cue built into light itself. As the universe expands, galaxies rush away from us, and the light they emit gets stretched toward longer, redder wavelengths. The faster they're receding, the more stretched their light becomes. By measuring the stretching, astronomers can work out roughly how far away a galaxy is. Kirshner's team expected to find galaxies scattered throughout their survey volume the way you'd expect stars scattered across a clear night sky. Instead, they found what looked like a colossal gap. Across a spherical region of space, roughly 330 million light-years in diameter, there was almost nothing. To put that scale in perspective, our nearest large galactic neighbor, the Andromeda Galaxy, sits about 2.5 million light-years from the Milky Way, and that gulf already feels almost incomprehensibly vast when you first learn about it. The Bode's Void could swallow more than 100 gaps that size back to back and still have room left over. Based on the average density of galaxies elsewhere in the universe, astronomers calculated that a region this size should contain somewhere around 2,000 galaxies. Instead, decades of searching turned up only about 60, and even those seemed to be arranged in a strange, narrow filament threading through the void rather than being spread evenly throughout it, almost like a thin bridge crossing an empty canyon. This discovery led to one of the more delightful thought experiments in modern astronomy. The astronomer Greg Aldering once pointed out that if the Milky Way had happened to form near the center of the Bode's Void, instead of where it actually sits, on the edge of a much richer, more crowded region of the cosmic web, human beings would not have discovered the existence of other galaxies until the 1960s. Our night sky would have been almost completely dark beyond our own galaxy's stars. No faint smudge of Andromeda visible to the naked eye. No neighboring galaxies for our earliest telescopes to resolve. Entire generations of astronomers, philosophers, and stargazers would have looked out at a universe that appeared, as far as they could tell, to consist of nothing but a single isolated island of stars, floating alone in an infinite black sea. It's a genuinely unsettling thought. Our entire understanding of the universe's scale and structure might never have developed in the way it did, simply because of where, by cosmic accident, our galaxy happened to be born. Voids like Bode's aren't uniformly barren either, and this is one of the more surprising things astronomers have learned about them in recent years. The handful of galaxies that do exist inside large voids tend to be strange in their own right. They're often dwarf galaxies, smaller and dimmer than the giants that populate the crowded filaments and clusters of the cosmic web, and they tend to be gas-rich, still actively forming new stars, almost as if the isolation of the void has slowed down their evolutionary clock. Some researchers studying so-called void galaxies have found that, freed from the gravitational shoving and merging that shapes galaxies in denser regions, these lonely systems can preserve a kind of primordial simplicity, offering a rare glimpse of what galaxy formation might look like with almost none of the usual crowding and interaction. In a strange way, the emptiest regions of the universe have become natural laboratories for understanding galaxy evolution, precisely because so little happens there. Nothing interferes, nothing collides. A void galaxy can go for billions of years essentially unbothered, its evolution shaped almost entirely by its own internal physics, rather than by neighbors tugging at it gravitationally. But the boat is void, as enormous as it is, has since been surpassed. Wider, deeper surveys of the sky have revealed structures that dwarf it. One such candidate, sometimes referred to as a supervoid, was found using data from the Pan-STARRS telescope in Hawaii, combined with observations from NASA's WISE space telescope, and it stretches across an almost unbelievable 1.8 billion light-years. What makes this particular void so scientifically interesting isn't just its size, but its position. It appears to line up almost perfectly with something called the cold spot, a strangely chilly patch discovered in the cosmic microwave background, the faint afterglow of radiation left over from the Big Bang itself. The idea is that as light from more distant galaxies travels through this enormous void on its way to us, it has to climb out of a very slightly weaker gravitational well, and in doing so, it loses a tiny bit of energy, cooling ever so slightly. Some researchers have speculated that a void this size could even be explained by exotic physics, perhaps even an unimaginably massive ancient black hole formed in the earliest fractions of a second, after the Big Bang, though this remains a highly speculative idea rather than an established explanation, and most cosmologists still favor more conventional structure formation processes to account for it. There's also an older, less famous contender worth mentioning, simply called the Giant Void, identified back in 1988 in the northern sky. For years, it held its own claim to being one of the largest structures known, containing around 17 galaxy clusters, scattered thinly across a spherical region, roughly 160 million light years across. It's a useful reminder that the hunt for the universe's emptiest places has been going on for decades, quietly running in parallel with the more celebrated search for its densest, brightest structures, and that our catalog of cosmic voids has only grown. Richer and stranger as survey technology has improved. Modern galaxy mapping projects like the Dark Energy Spectroscopic Instrument have been building three-dimensional maps of millions of galaxies with extraordinary precision. And as this data pours in, it continues to sharpen our picture of exactly how the cosmic web's walls, filaments, and voids are woven together, and how that structure has changed as the universe has aged. Now here is where the story takes its strangest and, frankly, most delicious turn. For years, cosmologists have been wrestling with a genuine crisis in their field, one that cuts right to the heart of how well we actually understand the universe's expansion. It's called the Hubble tension. When astronomers measure how fast the universe is expanding, using observations of the nearby, relatively local universe, things like pulsating stars, called Cepheids, and nearby supernovae, they get one number. When they instead calculate the expansion rate using the cosmic microwave background, that ancient light from the early universe, run through the standard cosmological model, they get a noticeably different number. These two methods should agree if our understanding of the cosmos is complete. They don't, and the more precisely astronomers measure both values, the more stubbornly the disagreement persists, rather than shrinking away as you'd expect from mere measurement error. Nobel laureate Adam Rees, whose work helped establish the accelerating expansion of the universe in the first place, has pointed out that better data keeps making this tension worse, not better. One of the boldest proposed solutions to this puzzle is almost poetic in its irony. What if the reason our local measurements of cosmic expansion look different from the global average is because we ourselves are living inside a void? Not the Buddha's void, not some far-off structure we'll never visit, but a vast, relatively empty region of space, centered roughly around our own cosmic neighborhood, sometimes called the KBC void, short for the astronomers Keenan, Barger, and Cowie, who first proposed evidence for it, or simply the local hole. According to this idea, the Milky Way, our sun, the solar system, everything we've ever known, might be sitting inside an underdense bubble roughly 1 billion light years across, or by some estimates even larger, on the order of 3 billion light years in diameter, with our position closer to its edge than its center. If this is correct, the physics gets genuinely fascinating. A region with less matter than average has weaker gravity holding things in place. Surrounding regions, which are denser and therefore exert a stronger gravitational pull, would tend to draw matter outward, away from the void's interior, the way water drains toward the deeper, heavier parts of a basin. Galaxies inside a void like this would appear to be receding from an observer at the center a little faster than they otherwise would, purely as a consequence of this outward gravitational flow layered on top of the universe's genuine overall expansion. An astronomer measuring the local expansion rate from inside such a void could easily mistake this extralocal push for a discrepancy in the fundamental physics of cosmic expansion itself, when in reality it would simply be a consequence of geography, of exactly where in the universe's vast structure we happen to be sitting. This isn't a fringe idea whispered about at the edges of astrophysics conferences. Research presented at the Royal Astronomical Society's National Astronomy meeting in 2025 revived and sharpened this hypothesis, with astrophysicist Indranil Banik and his collaborators calculating that a void of the right size and depth could boost the locally measured expansion rate by around 11% compared to the universe's true average, which happens to be almost exactly the size of the gap that has been puzzling cosmologists for the better part of a decade. It's an elegant, almost satisfying explanation. No need to rewrite the laws of physics, no exotic new particles or forces required, just the recognition that the universe is lumpier than our simplest models assume, and that we might be living in one of its emptier lumps. Of course, elegant does not automatically mean correct, and this remains a genuinely contested idea within the scientific community. Follow-up studies published throughout 2025, including detailed analyses using distance measurements from galaxy rotation surveys, have produced mixed results. Some research supports the existence of a substantial local underdensity and finds it broadly consistent with easing the Hubble tension. Other studies argue that a void deep and wide enough to fully explain the tension should have left clearer fingerprints in independent measurements of local galaxy motions, fingerprints that haven't been unambiguously found yet. The honest scientific picture right now is one of active, ongoing debate rather than settled consensus. It's entirely possible that a modest local void exists and explains part of the puzzle, while other factors, perhaps subtle errors in our distance measuring techniques or genuinely new physics we haven't yet identified, account for the rest. But set aside the unresolved debate for a moment and sit with the sheer strangeness of the proposal itself. It suggests that the ground beneath your feet, the star that warms your planet, the galaxy that cradles your entire civilization, might not be floating in a representative, average patch of the universe at all. It might instead be drifting through one of the cosmos's great empty basins, a region shaped like a bubble in the froth of the cosmic web, simply because that is where, by pure chance, matter happened to be a little sparser billions of years ago when the first tiny density fluctuations in the infant universe began to grow under gravity's patient pull. Regions that started out slightly denser than average pulled in more matter over time and grew into today's superclusters and filaments. Regions that started out slightly less dense fell further and further behind, ballooning instead into voids, their meager contents draining outward toward the emerging walls of galaxies, leaving behind ever emptier interiors. It's a process astronomers sometimes compare to bread dough rising. Tiny variations in the initial mixture become the bubbles in the solid structure of the finished loaf, magnified enormously over time. So what would actually happen if you could fall into the very heart of one of these voids, whether it's the ancient, well-studied Bota's void, the record-breaking supervoid tied to the cosmic microwave background's cold spot, or possibly unsettlingly, the very void some scientists think we already call home? The first thing to understand is that a cosmic void isn't a void in the way an empty room is empty. There's no wall, no boundary, no dramatic threshold you'd cross, no sudden vacuum sucking the air from your lungs, because there was never any air out there to begin with, and there wouldn't be any inside a void either. Interstellar and intergalactic space is already an almost perfect vacuum, whether you're near a bustling galaxy cluster or in the emptiest void ever mapped. What changes as you move deeper into a void isn't the vacuum itself, but the population of galaxies scattered through it, and even that change happens, gradually, not with any sharp edge. If you drifted deep into the heart of the Boat's void, your night sky would transform dramatically over what would, admittedly, be an absurdly long journey given the void's staggering size. The familiar band of the Milky Way would vanish behind you as you left our galaxy far in the rearward distance. Nearby galaxies would shrink to invisibility. Eventually, you would reach a point where the nearest galaxy might be tens of millions of light years away in any direction, its light so faint after that immense journey that it would be utterly invisible to the naked eye. A target only the most sensitive telescopes could hope to detect. Look up, and you would see stars, technically, because the void isn't devoid of all matter. Sparse foreground stars and rogue objects can still exist along the way, but no glowing spiral arms, no smudges of distant galaxies, no soft haze of the zodiacal light we take for granted from Earth. Just a profound, star-flecked blackness stretching in every direction, a darkness so deep and so total that it's genuinely difficult for a human mind, evolved on a planet nestled among galaxies, to properly picture it. The physical sensations, strange as it sounds, would be almost non-existent. There's no atmosphere to feel rushing past you, no sound to hear, since sound needs a medium like air to travel through, and there is, essentially, none out there. There's no sense of falling in the way you feel falling toward the ground on Earth, because in the near-total absence of nearby massive objects, there would be nothing pulling on you strongly enough to create that familiar sensation of acceleration. You would simply drift, weightless and silent, through kilometer after kilometer, then light year after light. Year of cold, dark vacuum, your only company, the faint, ancient photons of the cosmic microwave background itself, the leftover glow of the Big Bang, bathing you in a whisper of radiation so faint and so stretched out by the universe's expansion that it would be utterly invisible without specialized instruments. Even the temperature of that background glow drops as the universe expands, meaning that far in the future, deep inside a growing void, that whisper would fade further still, leaving an environment closer to absolute darkness and absolute cold than almost anywhere else that could be described as a location. There is something almost paradoxical about how such isolation would reshape your perspective on the universe itself, echoing back to Greg Aldering's thought experiment about a civilization born inside the Buddhist void. From deep within a supervoid, you would have essentially no direct visual evidence that other galaxies even exist. If intelligent life had evolved on a hypothetical world drifting in the void's exact center, their scientists might have spent centuries debating whether the universe consisted of anything at all beyond their own galaxy, utterly unaware that they were living inside a rare, cavernous gap in an otherwise richly structured cosmic web, a web whose existence they might never even suspect. It's a humbling reminder that our own picture of the universe, glittering with galaxies, stretching to the very limits of observable space, is itself a product of our specific cosmic address. Move the Milky Way to a different neighborhood, and the entire history of human cosmology might have unfolded completely differently, delayed by decades, or perhaps by centuries. And there's a final layer to this story that makes it feel even stranger, tied to the ultimate fate of these enormous cosmic bubbles. Because the universe's expansion appears to be accelerating, driven by the mysterious pressure we call dark energy, voids are not static features frozen in place. They're growing. As galaxies and clusters continue drifting apart from each other across cosmic time, the empty regions between them stretch and swell, while the galaxies themselves become ever more isolated within their own local clusters, gravitationally bound tightly enough to resist the expansion, pulling everything else apart. Cosmologists projected that in the almost unimaginably distant future, tens of billions of years from now, voids like the ones we've been discussing will have grown so vast and galaxies so gravitationally isolated within their own clusters that any civilization looking outward from inside one of these far future galactic islands might see nothing at all beyond their own local group, the rest of the observable universe having been carried beyond the cosmic horizon by the relentless stretching of space itself, its light forever unable to catch up and reach them. In some very real sense, the entire universe is slowly, gradually becoming more like the Buddhist void everywhere, not just in a few scattered pockets. Emptiness, on the grandest scales, is not the exception in the cosmos. It is the destiny. So the next time you look up at a clear night sky, dense with the faint light of countless stars, remember that this abundance is not a universal constant. It is a local privilege, granted to us by our particular address within the sprawling architecture of the cosmic web. Somewhere out there, whether millions or billions of light years away, or possibly, if certain cosmologists are right, cradling our own galaxy at this very moment, vast bubbles of near total emptiness drift through space, largely indifferent to the matter clustered at their edges. We may already be riding gently through the outskirts of one, our entire cosmic neighborhood subtly nudged and stretched by the gravity of the denser structures that surround it, quietly rewriting our estimate of how fast the universe expands in the process. And if that's true, then in a very real sense, we don't need to imagine falling into the biggest void in the universe at all. We may simply need to look more carefully at where we already are,